Robert Chin's flashlight beam caught the connector and his world stopped. MS-3106, a series. American military standard. He'd seen it 1,000 times in classified reports, always in American aircraft, never in anything Chinese or Soviet. Yet here it was. Nestled in the electrical bay of a Nanchong Q-5 attack aircraft that should have been pure communist engineering. Summer 1986. A secured hangar in Nevada, part of a facility so classified it didn't appear on any official map. The concrete structure, painted dusty tan to match the surrounding desert, looked unremarkable from outside. Inside sat something that should have been impossible to obtain. A complete Chinese Q-5 attack aircraft, acquired through channels so sensitive that even decades later, the full story remains partially classified. Chen's fingers traced the wire routing. Wrong. All wrong. Chinese aircraft followed Soviet conventions, learned from German engineers after World War II. Refined through decades of MiG production, it's followed completely different logic. Bending and turning through the airframe in patterns that tugged at his memory without quite resolving into recognition. A second-generation Chinese-American whose parents fled Shanghai during the 1949 revolution. Chen had built his career understanding the technology of the nation his family escaped. His expertise in Chinese and Soviet avionics was unmatched in Western intelligence. He'd written the definitive classified assessments of Chinese radar systems. Military planners consulted him routinely. He knew these patterns intimately, could recognize Soviet wiring methodology as easily as a native speaker recognizes their mother tongue. This wasn't Soviet. This wasn't Chinese.
Patterson, get over here.
William Patterson crawled under the Q-5's fuselage into the cramped inspection space. Former Air Force, 3 years at Korot Air Base in Thailand, maintaining F-105 Thunderchiefs during the height of the Vietnam War. If anyone could confirm what Chen was seeing, it was Patterson. Patterson took the flashlight. 5 seconds. 10. His expression shifted from curiosity to recognition to something close to shock. "That's thud wiring," he said quietly, using the F-105's nickname. "I've worked on this exact harness. Placed these connectors at Korot in 67 and 68. The pin configuration. Strain relief. Even the routing through the hydraulic bathe. This is copied straight from the 105 Thunderchiefs." The two analysts locked eyes. They'd spent careers dissecting MiG fighters from defecting pilots, analyzing Soviet missile fragments from crash sites, decoding technological secrets through painstaking examination of captured hardware. They thought they'd seen everything the communist world could produce. In that Nevada hangar, they'd just stumbled onto one of the Cold War's most significant secrets: American technology from crashed Vietnam. War aircraft had been systematically reverse-engineered and incorporated into Chinese military jets for nearly 2 decades. The hangar's climate control hummed, maintaining perfect conditions to preserve the aircraft's systems necessary in a facility where summer temperatures routinely exceeded 110 degrees Fahrenheit. Fluorescent lights cast harsh illumination across the Q-5's silver-gray fuselage, revealing every rivet in unforgiving detail. The aircraft sat on a specialized cradle, allowing full underside access. Surrounded by rolling tool cabinets and diagnostic equipment representing the cutting edge of 1980s reverse engineering capability, Chen and Patterson had been conducting routine technical documentation that morning, part of a months-long examination expected to produce thousands of pages of classified reports. The inspection team included metallurgists analyzing structural components, propulsion specialists examining the engine, weapons analysts evaluating offensive capabilities. Their task: document every aspect of the Q-5's design, assess its capabilities and limitations, identify any technologies that might threaten American forces. Nobody expected to find American military components. Chen's methodology was meticulous, almost ritualistic. He began every examination at the same point: the main wiring harness distributing power and signals through the fuselage. Wiring revealed more about an aircraft's design philosophy than almost any other component. The choices made in wire gauge, insulation material, connector type, and routing pattern told stories about the engineering culture that produced the aircraft, the manufacturing capabilities available to its builders, the operational requirements it was designed to meet. The connector Patterson now examined was unmistakably derived from designs he'd worked with at Korot. The pin configuration was identical. The latching mechanism was a faithful copy. Even small details like the strain relief features preventing wire damage from vibration matched his memories from the F-105. The color coding was perhaps most disturbing. Chinese aircraft wiring traditionally followed Soviet conventions, which themselves derived from German standards acquired after World War II. These colors didn't match those conventions. They matched American military specifications from the 1960s. What followed that discovery would launch an intensive investigation spanning months of classified research. Analysts would eventually piece together the full story of how F-105 wiring made its way into the Q-5, a story of downed American pilots, recovered wreckage, patient Chinese engineering, and the long shadow of the Vietnam War extending into the 1980s and beyond. But to understand how this happened, we must travel back to the skies over North Vietnam in the 1960s, where the F-105 Thunderchief earned its fearsome reputation and paid a terrible price. The Republic F-105 Thunderchief was designed for nuclear war. American military planners in the 1950s believed future conflicts would be decided by nuclear weapons. Delivered at supersonic speed, the F-105 was conceived as a nuclear strike platform capable of penetrating Soviet air defenses at low altitude and high speed to deliver a nuclear weapon against strategic targets. Its design reflected this mission. A powerful Pratt & Whitney J-75 engine pushing the aircraft past Mach 2, a sophisticated internal navigation system guiding it deep into enemy territory, and an internal weapons bay accommodating a nuclear device. The aircraft was massive, over 50,000 pounds fully loaded. Pilots quickly discovered it handled more like a bomber than a traditional fighter, requiring careful energy management to extract maximum performance. But what the Thunderchief lacked in agility, it compensated with raw capability. It could carry more ordnance than any fighter of its era, deliver that ordnance with devastating precision, and survive damage that would have destroyed lighter aircraft. When the Vietnam War escalated in 1964, the Air Force desperately needed aircraft for conventional bombing missions against North Vietnam. The F-105, despite being designed for nuclear delivery, was pressed into service as a conventional strike aircraft, a role it would dominate. Through pilot courage and robust airframe engineering, between 1965 and 1970, F-105s flew the majority of strike missions against North Vietnam under Operation Rolling Thunder. Each mission sent them into a gauntlet of surface-to-air missiles, anti-aircraft artillery, and MiG interceptors. They could carry 14,000 pounds of bombs while maintaining the speed and maneuverability needed to survive heavily defended airspace. The cost was staggering. North Vietnamese air defenses, supplied and advised by the Soviet Union, took a fearsome toll. The SA-2 guideline surface-to-air missile proved particularly lethal, forcing aircraft to fly at altitudes that brought them into range of concentrated 23mm and 37mm anti-aircraft fire. During the Vietnam War, 334 F-105s were lost to enemy action, nearly half of all Thunderchiefs ever built. One aircraft lost every 3.8 days of rolling thunder. The attrition rate was unprecedented in modern air warfare. Some aircraft were destroyed outright, vaporized by SA-2 direct hits, or torn apart by flak. Others went down slowly, pilots nursing crippled aircraft toward the coast hoping for rescue. Some ejected over the Gulf of Tonkin where Navy helicopters could reach them. Others went down over enemy territory, facing capture or death. Patterson had watched friends disappear into that meat grinder. Jake Morrison, his bunkmate at Corette, had gone down in F-105D serial number 610217 near Than Ho in April 1968. They never recovered his body. Patterson had personally signed off on that aircraft's pre-flight inspection. He'd checked those wire connections, verified those systems were operational. Now, 18 years later, he was staring at those same systems in a Chinese attack aircraft. For every F-105 that went down over North Vietnamese territory, there existed the possibility that wreckage might yield technological intelligence to the enemy. American planners understood this risk abstractly, but the intensity of the air campaign left little room for systematic consideration of long-term implications. The immediate priority was destroying targets and reducing losses, not worrying about what happened to aircraft that didn't return. The North Vietnamese, however, were thinking very carefully about exactly that question. November 3, 1967, 14:30 hours local time. F-105D serial number 624284. Call sign Falcon 3 took an SA-2 missile over Hanoi. Major Thomas Evans ejected successfully and was captured. The aircraft, its right wing torn away, plowed into a rice paddy 8 kilometers northeast of the city. Within hours, a Vietnamese People's Army recovery team reached the crash site. These weren't ordinary salvage workers. They were trained technical intelligence specialists armed with cameras, measurement tools, and Soviet-printed identification guides for American aircraft components. Their commander, Senior Lieutenant Nguyen Van Thru, had studied aircraft recognition at a military academy outside Moscow. He knew what to look for. The team worked through the night by lamplight, cutting away wiring harnesses with bolt cutters, photographing junction boxes, cataloging every connector. The fuselage had broken in half on impact, exposing the aircraft's internal systems and cross-section. It was like having an exploded technical diagram laid out before them. By dawn, key components were crated and heading to Hanoi's Military Technical Institute. By the end of the week, they were on a train to China. From the first American aircraft shot down over their territory, Hanoi recognized that downed aircraft represented intelligence gold mines. Specialized recovery teams were organized to reach crash sites quickly, salvaging whatever components might prove valuable for technical analysis. These teams faced considerable challenges. Aircraft often crashed in remote jungle terrain difficult to access. Wreckage was frequently scattered over wide areas, and fires consumed much of what remained. Nevertheless, the North Vietnamese proved remarkably effective at recovering significant components. Their primary interest was intact systems, radar equipment, electronic countermeasures, weapons targeting systems, and the sophisticated avionics, giving American aircraft their technological edge. These components were carefully extracted from wreckage, cataloged and transported to evaluation facilities in Hanoi. Their teams of technical specialists, some trained in the Soviet Union, examined the recovered equipment in exhaustive detail. What most American intelligence analysts didn't fully appreciate was the extent to which this recovered technology was being shared with North Vietnam's allies, particularly the People's Republic of China. The relationship between China and North Vietnam during this period was complex, strained by competing interests and mutual suspicion. The two communist nations were bound by ideology and geography, sharing a long border and a common enemy in American-backed South Vietnam. But they were also rivals for influence in Southeast Asia. And China's relationship with the Soviet Union, North Vietnam's primary patron, had deteriorated into open hostility. By the mid-1960s, the Sino-Soviet split transformed communist international relations. What had been a unified bloc under Soviet leadership fractured into competing camps. With China and the Soviet Union, each seeking to position itself as the leader of international communism, this rivalry played out in Vietnam, where both nations provided military aid to Hanoi while competing for influence. Despite these tensions, China provided substantial military assistance to North Vietnam during the American bombing campaign. Chinese anti-aircraft units deployed to North Vietnam to supplement local defenses. Chinese weapons, ammunition, and supplies flowed south along routes that became known as the Ho Chi Minh Trail. Chinese engineering units helped repair bomb damage to critical infrastructure. In return, China received access to something it desperately wanted: Western military technology captured from downed American aircraft. The Chinese aerospace industry in the 1960s was struggling with the consequences of technological isolation. China had broken with the Soviet Union in 1960, and Moscow responded by withdrawing technical advisors and halting the transfer of advanced aircraft designs. Chinese engineers were left to develop indigenous capabilities, largely on their own, working from outdated Soviet blueprints and whatever technology they could acquire through other means. The immediate impact was severe. China's most advanced fighter, the J-6, was a license-built copy of the Soviet MiG-19 itself, a design dating from the early 1950s. More advanced aircraft designs remained beyond Chinese capabilities. The factories and research institutes supposed to develop next-generation aircraft found themselves without the technical support and design data they needed to move forward. Into this difficult situation came the unexpected windfall of American aircraft wreckage from Vietnam. Here was access to the most advanced Western aviation technology of the era, delivered in quantity by the fortunes of war. The Chinese moved quickly to exploit this opportunity, recognizing that recovered American technology could help them leapfrog years of indigenous development. Beginning in 1965, specialized Chinese technical teams were dispatched to North Vietnam to assist in the recovery and analysis of downed American aircraft. These teams focused particularly on the F-105, which combined advanced avionics with robust, well-designed mechanical systems. The Thunderchief represented exactly the kind of practical, operational technology that Chinese engineers could study and adapt to their own programs. The wiring systems of the F-105 represented a specific area of American technological superiority that the Chinese were determined to understand and replicate. Aircraft wiring might seem mundane compared to radar systems or jet engines, but in practice, reliable wiring is essential to aircraft performance and safety. Electrical failures cause catastrophic accidents. The quality of an aircraft's wiring architecture often determines how reliably its more sophisticated systems perform. American aircraft wiring in the 1960s was a highly refined discipline, a product of decades of development and hard-won experience stretching back to World War II. The wire bundles in an F-105 were designed to be lightweight, resistant to electromagnetic interference, and capable of reliable operation under extreme conditions of temperature, vibration, and combat stress. The routing of these wiring harnesses was equally sophisticated. American engineers had developed optimized pathways that minimized wire length while protecting critical circuits from damage. Wires carrying sensitive signals were separated from power cables to prevent interference. Redundant pathways ensured that damage to one section wouldn't disable critical systems. The entire architecture reflected decades of refinement in response to operational experience. Connector designs incorporated features that prevented accidental disconnection, ensured reliable electrical contact under vibration, and protected against moisture and contamination. The MS-3106 series connectors used throughout the F-105 featured precision-machined aluminum shells, gold-plated contacts for corrosion resistance, and hermetic seals protecting internal connections. Even the color coding of individual wires followed carefully developed standards, facilitating maintenance and troubleshooting. A maintenance technician could trace any wire through the aircraft simply by following its distinctive color pattern: white with red tracer for 28 volts DC primary power, yellow for lighting circuits, blue for instrument power. For Chinese engineers working with more primitive domestic technology, it's represented exactly the kind of incremental but critical advancement that could accelerate their programs by years. Chinese aircraft of that era suffered from persistent electrical problems, shorts, connector failures, and electromagnetic interference degrading avionics performance. American wiring technology offered solutions to problems Chinese engineers had struggled to solve independently. The recovery teams in North Vietnam documented everything they found in F-105 wreckage. Wire samples were collected for laboratory analysis of materials and manufacturing techniques. Connectors were carefully disassembled to understand their design features. The routing of wiring through the airframe was photographed and measured. All of this information was compiled into technical packages transmitted back to aerospace facilities in China. The Nanchong Aircraft Manufacturing Corporation, located in Jiangxi Province in southeastern China, was the primary recipient of this recovered technology intelligence. Nanchong was developing what would become the Q-5 attack aircraft, China's first indigenous jet designed specifically for ground attack missions. The Q-5 program had begun in 1958. In the optimistic early years of Chinese communist rule, when ambitious industrial programs promised to rapidly modernize the nation, the original concept called for creating a dedicated attack variant of the J-6 fighter. Mighty's copy of the Soviet MiG-19. Modifications would include a revised nose section with improved pilot visibility, an internal weapons bay for carrying bombs, and enhanced armor protection for low-altitude operations. Chief designer Liu Xiaopeng led the engineering team tasked with transforming this concept into reality. Liu was one of China's most talented aircraft engineers, a graduate of the Aviation Institute of Moscow who had returned to China to help build his nation's aerospace industry. I had worked on the J-6 program and understood both the capabilities and limitations of Soviet-derived designs. The initial phases of the Q-5 program proceeded slowly but steadily. By 1960, The basic configuration had been established, and detailed design work was underway. Then came the break with the Soviet Union, which deprived the program of technical support and access to advanced components. Progress slowed dramatically as Chinese engineers struggled to solve problems that Soviet advisors would once have helped address. The chaos of the Cultural Revolution, beginning in 1966, dealt a further blow to the program. Liu Xiaopeng was among many technical specialists who faced persecution for their education and professional backgrounds. Red Guards accused him of being a capitalist rotor and foreign spy due to his Moscow education. He spent 6 months in a re-education camp before being recalled when technical problems threatened to derail the Q-5 program entirely. The program continued in a reduced state, but resources were scarce and political interference was constant. It was during this difficult period that recovered American technology began offering solutions to problems that had stymied the design team. At Nanchong, Liu Xiaopeng laid out recovered F-105 wiring harnesses on a light table. For 3 months, his team documented every millimeter. Wire gauge, American AWG-20, insulation temperature rating 200 degrees Celsius, substantially better than anything Chinese factories could produce. The challenge wasn't just copying, it was adapting American designs to Chinese manufacturing limitations. Chinese wire manufacturers couldn't replicate the Teflon insulation used in F-105 wiring. Liu's solution? Double wrap with Chinese polyimide and route wiring away from heat sources. Not ideal, but functional. Each connector was disassembled, measured with calibers accurate to 0.01 millimeters, and redesigned for Chinese tooling capabilities. Where American connectors use 24 precision pins, Chinese versions use 16 larger pins, achieving similar current carrying capacity with less precise manufacturing. The wiring systems from captured F-105 components were studied in exhaustive detail. Reverse engineering not just the physical components, but the underlying design philosophy. Engineers analyzed wire gauge selections, insulation materials, connector pin configurations, and routing methodologies. Where Chinese industry couldn't replicate American materials exactly, engineers worked to find acceptable substitutes, preserving critical performance characteristics. By 1969, Nanchong's production line was installing domestically produced wiring harnesses that were 87% faithful to American F-105 designs. The remaining 13% represented necessary compromises with Chinese industrial capacity. The result was a wiring architecture for the Q-5 that borrowed heavily from American practice. The routing patterns that would later catch Chen's attention were adapted directly from F-105 documentation. Connector types were copied or closely imitated. Even the color coding of individual wires followed American conventions rather than Soviet or Chinese standards. This wasn't the only technology that flowed from crashed American aircraft into Chinese aerospace programs. The Q-5's internal layout, its weapons bay design, and certain aspects of its avionics integration all showed evidence of influence from recovered Western technology. The aircraft that eventually emerged from Nanchong's factories wasn't simply a modified MiG-19. It was a hybrid design incorporating significant elements of American engineering alongside its Soviet foundation. The Q-5 made its first flight on June 4, 1965, with test pilot Tung Deju at the controls. The initial flight lasted only 15 minutes, but confirmed that the basic design was sound. The aircraft demonstrated acceptable handling characteristics and performance meeting initial requirements. However, development problems and the continuing chaos of the Cultural Revolution delayed the program for years. Technical difficulties with the aircraft's weapons bay and landing gear required redesigns. Political upheaval disrupted production schedules and diverted resources. It wasn't until 1970 that the Q-5 entered full production, and not until the mid-1970s that it achieved widespread service with the People's Liberation Army Air Force. By the time the Q-5 was operational, the Vietnam War had ended and the immediate flow of captured American technology had ceased. But the lessons learned from that technology were embedded in the aircraft's design, waiting to be discovered by American analysts if the opportunity ever arose to examine a Q-5 in detail. That opportunity came in the early 1980s, during an unexpected period of strategic cooperation between the United States and China. The two nations, though ideologically opposed and separated by decades of hostility, found common cause in their mutual opposition to the Soviet Union. The Soviet invasion of Afghanistan in 1979 alarmed Beijing, raising fears of Soviet encirclement. Washington, meanwhile, sought allies in its renewed confrontation with Moscow. Under the Reagan administration, the United States pursued a policy of supporting Chinese military modernization as a counterweight to Soviet power. This policy included sales of certain dual-use technologies, limited military exchanges, and intelligence sharing on Soviet capabilities and intentions. It was a remarkable reversal for two nations that had been bitter enemies just a decade earlier. This rapprochement created unusual opportunities for American intelligence. As part of the warming relationship, Chinese officials agreed to limited technical exchanges and eventually to providing samples of certain military equipment for American inspection. Stated purpose was facilitating cooperation, but for American intelligence analysts. It represented an unprecedented opportunity to examine Chinese capabilities firsthand. The acquisition of a complete Q-5 aircraft for technical analysis was one fruit of this peculiar Cold War détente. The exact circumstances of how this particular aircraft came into American hands remain classified, but intelligence community sources confirmed that the transfer occurred through official channels as part of the broader Sino-American cooperation of the period. By summer 1986, the Q-5 had arrived at the classified Nevada facility, where it awaited examination by CIA technical specialists. The facility, part of a complex that had hosted similar examinations of Soviet equipment for decades, was perfectly equipped for the task. The inspection proceeded methodically through its first weeks. The aircraft was photographed from every conceivable angle, with particular attention to surface features revealing manufacturing techniques and quality control standards. Precise measurements documented the aircraft's dimensions and confirmed Chinese reporting of its specifications. Gradually, the Q-5 was disassembled for detailed examination. Panels were removed to expose internal structures. Access doors were opened to reveal the engine bay, weapons compartment, and avionics installations. Each component was photographed, cataloged, and examined against databases of known Chinese and Soviet manufacturing practices. It was during the examination of the aircraft's electrical systems that Chen began noticing the anomalies that would ultimately lead to the investigation's most significant findings. His initial assumption, when he noticed the unfamiliar routing patterns and connector types, was that he might be seeing influence from Western commercial aviation technology. China had begun importing civilian aircraft and spare parts from Western nations during the 1970s. And some technology transfer from these commercial sources into military programs wouldn't have been surprising. But as Chen traced the wiring patterns deeper into the aircraft, the similarities became too specific and too detailed to be explained by general Western influence. These weren't generic Western practices. They were specific design choices matching particular systems Chen had seen documented in his years of intelligence work. When Patterson joined the examination and immediately recognized F-105 wiring configurations, the scope of what they'd discovered became clear. The technology transfer wasn't general, it was specific and traceable. Chinese engineers hadn't merely adopted Western practices. They had directly copied American military systems from crashed aircraft recovered 2 decades earlier. The discovery launched an intensive investigation that continued for months after the initial examination concluded. Intelligence analysts pulled records of every F-105 lost over North Vietnamese territory, identifying probable crash sites and assessing which aircraft might have provided recoverable components. 334 aircraft? They needed to narrow it down. Chen focused on the wire color coding a specific variant introduced in late 1966 for F-105D aircraft in Operation Rolling Thunder that eliminated early war losses. Patterson identified a routing modification around the hydraulic BAA field, modification implemented at Koret Air Base in mid-1967 after a series of fires caused by chafed wiring. The database searches converged. F-105Ds lost between June 1967 and December 1968 over areas accessible to Chinese recovery teams. 17 aircraft fit the parameters. Then came the breakthrough. Connector in the Q-5's avionics bay bore a faint manufacturer's stamp. USAF the 14th of March 67, manufactured March 14, 1967, cross-referencing. Pentagon procurement records showed that batch went to F-105Ds with serial numbers 624371 through 624384. Aircraft 624371 shot down. March 22, 1967, near Hanoi. Pilot captured. Aircraft largely intact on impact. Probable candidate. Aircraft 624284 shot down November 3, 1967, near Hanoi. Pilot captured. Aircraft broke in half, exposing internal systems. Highly probable candidate. That's it, Chen said, examining the connector under magnification. That's our bird. Cross-referencing specific features observed in the Q-5 with modifications implemented during particular time periods allowed analysts to narrow down likely source aircraft with remarkable precision. Certain connector designs and wiring routing patterns matched modifications that had been implemented in F-105s. During specific maintenance cycles at specific bases, the investigation revealed that the technology transfer had been far more extensive than anyone initially imagined. Beyond the wiring systems, analysts identified other components and design features in the Q-5 showing clear evidence of American origin. Cooling system design employed principles from F-105 thermal management systems. Certain structural features around the weapons bay mirrored American stress skin construction techniques rather than Soviet methods. Elements of the cockpit layout, particularly the instrument panel organization and circuit breaker arrangement, demonstrated influence from recovered American technology. The Q-5 wasn't simply a modified Soviet design. It was a hybrid incorporating significant elements of captured American technology. The aircraft's performance capabilities, reliability, operational flexibility all benefited from this technological infusion. Where the J-6 predecessor suffered from persistent electrical problems, the Q-5 demonstrated remarkable system reliability. Where Chinese aircraft had struggled with electromagnetic interference affecting avionics, the Q-5's careful wiring separation and shielding largely eliminated these issues. This discovery had profound implications for American intelligence assessments of Chinese capabilities. For years, analysts had assumed that Chinese aerospace technology derived exclusively from Soviet sources. With whatever limitations that implied, the Q-5 examination demonstrated this assumption was dangerously wrong. Chinese engineers had proven themselves capable of exploiting recovered foreign technology effectively, integrating captured American components and design principles into their own programs. This suggested the Chinese aerospace industry was more sophisticated and more adaptable than previous assessments credited. The discovery also raised troubling questions about what other technologies might have been transferred through similar channels. The F-105 wasn't the only American aircraft lost over North Vietnam. F-4 Phantoms, F-8 Crusaders, A-6 Intruders, and various reconnaissance aircraft had also been shot down over enemy territory. What technology might have been recovered from those aircraft? Were there other Chinese systems incorporating American components that analysts simply hadn't examined closely enough to detect? For the intelligence community, the Q-5 wiring revelation became a case study in the dangers of assumptions and the importance of detailed technical examination. The analysts who had previously assessed Chinese capabilities had been working with incomplete information, missing a crucial piece of the puzzle that only became visible through hands-on examination of actual Chinese equipment. Overhead imagery could reveal aircraft dimensions and performance characteristics. Signals intelligence could provide information about radar and communications systems, but only physical examination could detect the subtle design choices revealing the true origins of technological capabilities. Going forward, intelligence assessments would need to account for the possibility that any American technology lost in combat might eventually appear in adversary systems. This realization influenced everything from aircraft design, which began incorporating features intended to complicate reverse engineering, to operational planning, which placed greater emphasis on preventing technology capture. Subsequent American aircraft incorporated self-destruct mechanisms for the most sensitive avionics components. Circuit boards were potted in epoxy compounds, making them nearly impossible to reverse engineer. Manufacturing techniques were deliberately obscured, for instance, using multiple suppliers for identical components, so that any single captured part wouldn't reveal systematic production methods. The assumption that any technology deployed in combat might eventually fall into adversary hands became a fundamental principle of defense acquisition. The story also highlighted the long-term consequences of combat losses extending far beyond the immediate tactical situation. Every F-105 that went down over North Vietnam represented not just the loss of an aircraft and possibly a pilot, but also the potential transfer of advanced technology to hostile powers. The full cost of those losses was only becoming clear decades later. For the engineers who had originally designed the F-105 systems, the discovery was deeply unsettling. Their work, created to give American pilots an edge in combat, had been studied, copied, and incorporated into an aircraft that might one day face American forces or allies in battle. The careful engineering that made the Thunderchiefs' electrical system so reliable had been turned against its creators. The Q-5 went on to become one of the most widely produced Chinese combat aircraft. With over 1,000 eventually built across multiple variants, various upgraded versions served with the People's Liberation Army Air Force for decades, providing China with a capable ground attack platform. The A-5C variant, introduced in 1983, featured improved avionics and weapons systems while retaining the fundamental airframe in its embedded American wiring architecture. Export variants of the Q-5 were sold to Pakistan, Bangladesh, Myanmar, and North Korea, spreading the aircraft's capabilities and its embedded American technology even more widely. Pakistan received approximately 50 aircraft beginning in 1983. Using them extensively in ground attack and close air support roles, Bangladesh operated the type for air defense suppression. Every one of these aircraft carried in its wiring and other systems the legacy of F-105s lost over North Vietnam. The technology that American engineers had developed to strike at communist forces had, through the fortunes of war, become part of the communist world's military capabilities and spread to nations around the globe. The irony wasn't lost on the analysts who pieced together this story. This pattern of technology transfer through captured equipment wasn't unique to the F-105 and Q-25. Throughout the Cold War, both sides exploited captured enemy technology whenever opportunity arose. The United States benefited enormously from German technology acquired after World War II, including jet engines, rocket designs, and radar systems that accelerated American military development by years. Operation Paperclip brought German scientists to America, where their expertise contributed directly to American aerospace advances. Soviet equipment captured during various conflicts, from Korean War MiG-15s to Egyptian air defense systems obtained in the 1970s, provided American engineers with invaluable insights into adversary capabilities. The Soviet Union similarly exploited captured Western technology. A B-29 bomber that made an emergency landing in Soviet territory during World War II was reverse-engineered to produce the Tupolev Tu-4, giving the Soviets a strategic bombing capability they wouldn't otherwise have achieved for years. Western electronics recovered from various sources found their way into Soviet avionics systems throughout the Cold War. What made the Q-5 case notable was its demonstration of how effectively its developing nation could exploit such opportunities. China in the 1960s lacked the industrial base and technical expertise, characterizing the American or Soviet aerospace industries. But Chinese engineers proved remarkably adept at identifying valuable technologies in captured equipment and adapting them to their own purposes. This adaptability would prove to be a defining characteristic of Chinese industrial development, visible not just in aerospace, but across the entire economy. For American military planners, the Q-5 revelation reinforced the importance of technology protection in all its forms. The specific individuals involved in the original technology transfer, both Chinese and Vietnamese, have largely remained anonymous, their identities protected by decades of secrecy. The Vietnamese recovery teams who salvaged F-105 wreckage were soldiers and technicians doing their duty under wartime conditions. The Chinese engineers who exploited that recovered technology were advancing their nation's military capabilities as best they could with the resources available. Their work, conducted in secrecy, has never been officially acknowledged by Beijing. Some records have emerged over the years, fragmentary accounts hinting at the scope of the effort. Chinese technical reports from the period describe systematic evaluation of American aircraft wreckage and identification of technologies suitable for reverse engineering. Vietnamese military histories mention specialized recovery units operating in areas where American aircraft frequently went down, suggesting an organized and sustained effort to salvage usable technology. But the full story remains partially buried in classified archives on 3 continents. Documents that might definitively establish the chain of custody for specific F-105 components remain locked away. Their continued classification, a testament to the sensitivity of the information they contain. Robert Chen and William Patterson, the analysts who first identified the F-105 wiring in the Q-5, went on to long careers in technical intelligence. Their discovery became a teaching example for future generations of analysts. Cautionary tale about the dangers of assumptions and the importance of detailed technical examination. Both men continued working on Chinese aerospace programs for years after the 1986 examination, bringing their hard-won insights to assessments of increasingly sophisticated Chinese aircraft. Chen became the CIA's senior expert on Chinese avionics systems, consulted on every major intelligence assessment of Chinese air capabilities through the end of the Cold War. Patterson transitioned to training new analysts, teaching them to look beyond the obvious and question their assumptions. Chen later recalled the moment of recognition in the Nevada hangar as one of the most significant of his career. In that wiring, he said, he could see the entire arc of the Cold War, American technology developed to counter the Soviet threat, deployed in combat in Southeast Asia, captured by North Vietnamese forces, transferred to China, and eventually incorporated into Chinese military capabilities. The copper and insulation told a story spanning decades and continents. Every wire told a story, Chen said in a rare interview years after his retirement. American engineers in the 1950s solving problems they thought would help win a war against the Soviet Union. Those solutions ending up in Chinese aircraft that might face American pilots. Technology doesn't respect borders or ideologies. It just flows to whoever can use it. Patterson, for his part, found the experience bittersweet. The aircraft he'd helped maintain at Koret, the F-105s he'd kept flying through years of combat, had left a legacy he never anticipated. Some part of those aircraft, some echo of the work he and his fellow maintainers performed under the tropical sun of Thailand, lived on in Chinese military aviation. Jake Morrison and I used to work on these systems together, Patterson reflected. We'd trace wiring faults through the aircraft, sometimes working through the night to get birds ready for morning missions. Jake didn't come home. His aircraft went down in '68. Now I find out that some piece of what we built, what we maintained, ended up in a Chinese fighter. It's not the immortality any of us sought. But Patterson also recognized the larger lesson. Technology is neutral. Once it exists in the world, it belongs to whoever can master it. Our job as intelligence analysts isn't to judge that reality. It's to understand it and account for it in our assessments. That's what we failed to do with China. We assumed their technology was purely Soviet-derived. We assumed wrong. The Q-5 remained in service with the People's Liberation Army Air Force until well into the 21st century, a remarkably long service life for a design tracing its roots to the 1950s. The aircraft underwent numerous upgrades over its career, with improved avionics, weapon systems, and engines. But its basic architecture remained recognizable through all these modifications. The final Q-5 South were retired from Chinese service only in 2017, replaced by more modern attack aircraft reflecting China's dramatically improved aerospace capabilities. By that point, the Q-5 was an anachronism, a relic of an era when China had to rely on captured enemy technology to advance its military programs. The aircraft that replaced the Q-5 in Chinese service are far more sophisticated products of a Chinese aerospace industry that has advanced enormously since the days when engineers relied on recovered enemy wreckage for technological inspiration. Modern Chinese fighters like the J-20 stealth fighter and J-16 multi-role fighter incorporate advanced technology rivaling Western capabilities. These aircraft feature sophisticated avionics, precision weapons, advanced engines, and stealth characteristics developed through a combination of indigenous research and extensive cyber espionage operations. The long road from the Q-5 to these modern aircraft is a testament to the cumulative nature of technological development. Yet even as Chinese aerospace technology has advanced, the fundamental dynamic revealed by the Q-5 story remains constant. The competition for technological advantage continues, and the efforts to acquire, protect, and exploit military technology remain central to great power competition. The methods have evolved dramatically, moving from physical recovery of wreckage to cyber espionage, supply chain infiltration, and sophisticated intelligence operations, but the underlying impulse remains the same. In 2015, the U.S. Department of Justice indicted 5 Chinese military officers for cyber espionage targeting American defense contractors, including companies working on the F-35 fighter program. The indictment alleged that Chinese hackers stole technical data on aircraft designs, engine technology, and avionics systems. It was the Q-5 story playing out in digital form, the same strategic logic applied with 21st-century tools. In military aviation museums around the United States, restored F-105 Thunderchiefs stand as monuments to the courage of the pilots who flew them and the sacrifice of those who didn't return. At the National Museum of the United States Air Force in Dayton, Ohio, magnificently restored F-105D stands in the Southeast Asia War Gallery, surrounded by artifacts and photographs from the Vietnam era. Visitors walk past, admiring its sleek lines and reading plaques describing its combat history. The museum display mentions the 334 aircraft lost in combat, the dangerous missions flown into the teeth of North Vietnamese defenses, the pilots who earned medals of honor flying the type. What those museum displays don't reveal is the afterlife of the aircraft that didn't make it home the journey that took them from the jungles of North Vietnam to Chinese engineering laboratories and eventually into the systems of a foreign combat aircraft. The F-105s on display represent survivors. Their fallen siblings live on in less visible ways, their technology scattered across the world's military aviation heritage. Few visitors pause to consider what happened to those 334 lost Thunderchiefs. Where did they come to rest?
Oh, what happened to their wreckage?
Did any of their technology survive? And if so, where did it go? The answers to those questions would surprise them. The story of the Q-5 and the F-105 wiring serves as a reminder that the consequences of war extend far beyond the battlefield and the immediate moment of conflict. The technology lost in combat can resurface years or decades later in unexpected places and unexpected forms. The prices paid by nations in conflict are measured not just in lives and treasure, but in the long-term implications of every piece of equipment that falls into enemy hands. For those who study military technology and intelligence, the Q-5 case offers lessons that remain vitally relevant today. The importance of protecting sensitive technology, the danger of underestimating adversary capabilities, the value of detailed technical examination rather than relying on assumptions, the need to trace the full life cycle of military equipment from design through deployment to potential capture and exploitation. As military competition continues evolving, these lessons continue to apply. The Cold War that produced this particular episode of technological espionage has ended, but the underlying dynamics of great power competition persist. Nations continue seeking technological advantages, and the efforts to acquire foreign military technology through whatever means available continue unabated. The specific techniques have evolved dramatically since the era of recovering aircraft wreckage from jungle crash sites. But the fundamental strategic logic remains unchanged. Modern technology acquisition takes many forms. Cyber operations can steal design data directly from corporate and government networks, providing complete technical specifications without the need to physically acquire hardware. Supply chain infiltration can introduce vulnerabilities or enable access to sensitive components during manufacturing. Academic exchanges and commercial partnerships can facilitate both legitimate and illegitimate technology transfer. The physical recovery of crashed aircraft has given way to digital infiltration, but the underlying competition for technological advantage continues with undiminished intensity. Understanding the history of cases like the Q-5 wiring helps illuminate these contemporary dynamics. The Chinese engineers who reverse-engineered F-105 systems in the 1960s and 70s were following the same strategic logic that drives technology acquisition efforts today. They recognized that access to advanced foreign technology could accelerate their own development, and they exploited every available opportunity to obtain that access. Their modern counterparts do precisely the same thing, using different tools but pursuing identical objectives. The Department of Defense now operates on the assumption that any technology deployed in any context may eventually be compromised. This assumption shapes acquisition strategy, operational planning, and technology protection efforts. Aircraft are designed with features intended to complicate reverse engineering. The most sensitive systems include mechanisms to destroy critical components if capture appears imminent. Manufacturing techniques are deliberately obscured to prevent adversaries from understanding production methods, even if they obtain components. But despite these efforts, technology continues to flow. In 2018, reports emerged that Chinese engineers had successfully developed a clone of the General Electric F-414 turbofan engine used in American F/A-18 Super Hornets. The engine, designated WS-19, bore remarkable similarities to the American design in dimensions, performance characteristics, and internal architecture. How Chinese engineers obtained the necessary technical information remains unclear, but the pattern was unmistakable, the same pattern Chen and Patterson had identified in that Nevada hangar 32 years earlier. In the end, the Q-5 wiring story is about more than just aircraft and electronics. It's about the relentless nature of competition between nations, the ingenuity of engineers working under difficult circumstances, and the interconnected nature of technological development. The wiring that traveled from an American aircraft factory in Farmingdale, New York, to the skies over Vietnam, to a Chinese aircraft manufacturer in Nanchong, and eventually to a CIA inspection facility in Nevada, traces a path through some of the most consequential events of the 20th century. The analysts who examined that wiring in 1986 were looking at more than just copper and insulation. They were looking at history, at the physical evidence of decades of conflict and competition. Their discovery added another piece to the complex puzzle of Cold War technological rivalry. A puzzle that historians and analysts continue studying and debating today. The F-105 Thunderchiefs and the Nanchong Q-5 represent very different approaches to military aviation. It's products of different industrial systems, different military philosophies, and different national circumstances. Yet they are forever linked by the wiring that connects them, a physical manifestation of how technology flows across boundaries, even between nations at war. That connection, discovered in a Nevada hangar nearly 4 decades ago, remains a powerful reminder of the complex and often unexpected ways that military technology evolves. The engineers who designed the F-105's electrical systems could never have imagined that their work would one day appear in a Chinese attack aircraft. The Chinese engineers who copied that work probably never expected that American analysts would identify their borrowing with such precision. Such are the strange twists of technological history, the unexpected connections emerging when the full story is finally told. The Q-5 wiring is one such connection, a thread tying together American innovation, Vietnamese determination, Chinese ingenuity, in the long shadow of the Cold War that shaped all their efforts. Today, in a climate-controlled storage facility in Nevada, the Q-5 that Chen and Patterson examined remains preserved. The aircraft sits in carefully maintained conditions, a historical artifact of a particular moment in the Cold War. The wiring that first caught Chen's attention remains intact, preserved as evidence of a remarkable journey. Occasionally, intelligence analysts visit the facility to examine the aircraft, using it as a teaching tool for new generations of technical specialists. The wiring still tells its story to those who know how to read it. That copper traveled further than any pilot who flew it, from American factories to Vietnamese jungles, from communist research laboratories to the heart of Chinese military aviation, from enemy skies back to American hands. Each bend, each connector, each color-coded wire represents a problem solved by American engineers in the 1950s, solutions that proved so effective they were worth copying 2 decades later by engineers on the other side of the world. Technology once released has no allegiance.
Right?
The engineers who designed the F-105's wiring built it to defeat communism. 2 decades later, it helped arm communist forces. This isn't irony. This is the nature of knowledge itself, neutral, transferable, unstoppable. Every wire, every connector, every routing choice represented a problem solved. Those solutions didn't care about flags or ideologies. They simply worked. And because they worked, they were worth studying, worth copying, worth incorporating into another nation's aircraft. The technology survived the aircraft, survived the war, survived the ideological conflict that produced it. The Cold War ended, the Soviet Union collapsed. The Q-5 retired, most participants are gone. But the fundamental competition continues, now measured in terabytes instead of copper. in network intrusions instead of crash site recoveries, in supply chain vulnerabilities instead of salvaged wreckage. Somewhere tonight, analysts examine foreign technology, looking for the anomaly that reveals the truth. Engineers protect secrets, knowing that today's advantage becomes tomorrow's vulnerability. Intelligence officers trace the flow of technology across borders, trying to understand what adversaries have acquired and how they acquired it. The cycle continues, unchanging in its essentials even as its manifestations evolve. The wiring remains in that Nevada facility, a small monument to larger truths. In the contest between nations, technology is the territory, and every battle leaves the map redrawn. Understanding this reality, accepting it without illusions, the first step toward navigating the complexities of technological competition in an interconnected world. Chen and Patterson understood this when they made their discovery in 1986, the copper and insulation. They examined that day, told a story that transcended the immediate intelligence value of their findings. It told a story about how the world actually works, about the permeability of boundaries that seem solid, about the unexpected paths that knowledge travels once it escapes into the world. That story remains relevant today, perhaps more relevant than ever. As nations compete for technological advantage in artificial intelligence, quantum computing, hypersonic weapons, and countless other domains, the lessons of the Q-5 wiring endure. Technology flows, adversaries learn, advantages erode. The competition never ends. The wiring that connected the F-105 to the Q-5 now connects past to present, offering insights for those willing to learn from history. In that connection lies wisdom for navigating the technological competitions of tomorrow. And in a hangar in Nevada, the evidence remains, waiting to teach its lessons to anyone who takes the time to listen.